5.3, independence and the multiplication rule. All right, so the first thing is look at independent versus dependent. So two events, E and F, are independent if the occurrence of event E in a probability does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So if they have no effect on each other, they're independent, but if one affects the other, they are dependent. So let's look at some examples. So let's suppose that we are flipping a coin and then rolling a die. And the events are obtain a head and roll a 5. Well, these are going to be independent because the rolling of the die does not affect the flipping of the coin or vice versa. With those, we'll still have those things independent of each other. Are the events earned a bachelor's degree and earn more than $100,000 per year independent? Well, no, because we know that an individual that has a bachelor's degree is more has an effect on the likelihood of making more than $100,000. It's not a guarantee, but it does have an effect with those pieces. Okay. And then the other example here, we have two 24-year-old male drivers. They're randomly selected. The events male 1 gets in a car accident and male 2 gets in a car accident. Those are independent because the males are randomly selected. We don't know where they're from, what's happening, any of those types of things on this. And so what this means is that what happens with one of the drivers has nothing to do with what happens to the other driver. And so they are independent of each other. Now another dependent one is pulling two cards from the same deck and not replacing. So if we take one card out, it's going to affect what our second card can be. And so that's another place that we look at being dependent. Okay. Now disjoints events and independent events are different concepts. Okay, so we've got to think of them differently than each other. And so two events are disjoint if they have no outcomes in common. That is, if knowing one of the events occurs, we know the other event did not occur. Independence means that one event occurring does not affect the probability of the other event occurring. Not that it did not occur. It just doesn't affect the probability. Okay? All right, the multiplication rule. So if E and F are independent events, so we know they're independent of each other, then E and F, the probability of E and F is the probability of E times the probability of F. Okay? All right, so in a game of roulette, we have a wheel with slots numbered 0, 00, and then 1 through 36. They roll a ball on a wheel and it falls into one of the numbered slots. What is the probability that a ball will land in the slot number 21 2 times in a row? Okay, so there are 38 possible outcomes. We have the numbers 1 through 36 and then 0 and 00. So that creates 38 possible outcomes. And so the probability of landing on a 21 is 1 out of 38. Because the events 21 on spin 1 and 21 on spin 2 are independent, then we can just simply multiply here. 1 over 38 times 1 over 38, and we get 1 over 1,444. Okay, so it's a very unlikely event, as we can see when we do this. Okay. All right, now we can continue that for multiple events. It doesn't just have to be 2. It can be for any number of events that happen there. Okay. All right, so what is the probability that 3 randomly selected 24-year-olds will survive the year based on the probability that surviving the year is 0.9986? And so for all 3 males, that would be the first survives, second, and third survives. And so we just multiply there. So 0.9986 times 0.9986 times 0.9986. Or 0.9986 to the third power. So if you remember there on that, we do 0.9986 to the power of 3. So this little housetop thing over here, right above the division sign, is our power number. And it's the third power because there are 3 of them. Okay. All right, so that's a 0.9958 probability that all 3 survive. Okay. What is the probability that 20 will survive the year? Okay. So it's the same thing. So again, we would do our 0.9986 and then to the 20th power here to get what we need for that one. All right. And make sure, again, we round appropriately. At least. So compute the probability at least 1 male out of 1,000 age 24 will die in the course of a year. Okay? For those. And so to do at least, we actually do 1 minus the complement, meaning none die with those. So anytime we're going to do an at least problem, you're actually going to flip it around and do 1 minus none die, or nothing happens with that, okay? Because we can't do all of the different combinations, but since none die is just a 0 there, it makes it easier for that, okay? All right, and so in this case, we would do 1 minus p to the 1 survive second, all the way up to the 1,000th, all right, for those, okay? And so we would be able to multiply those. Now there is a mistake here. They actually used the wrong thing. So this should not be 20. It should be 1,000, okay? It's a horrible looking 1,000, but I'm trying to draw on my screen here for those. But that's to the 1,000 power there for that, okay? So make sure that you put that in properly. If you do that to the 1,000 power, we would then get the 0.2464 and do 1 minus that number to get a 0.7536. So a 75% chance that out of 1,000, at least 1 will die. Okay? All right, and so just kind of a summary of our rules here. We've talked about these over the past few sections, so look over those and remember those types of things. Those are the different formulas and things that you're going to need in order to look at these probabilities and paying attention to what is going on there, okay? All right, so those are the things that you're going to need there in 5.3.